Welcome! So today we are going to do multivariate calculus tutorial number 2, and in this tutorial that will all be about calculating partial derivatives and using some very basic applications. All right, so if you're interested in that, then stay tuned. So what you see above my head there is a graphic of the function f of x and y equal to 1 minus x squared minus y squared. So a very basic function of two variables. And so what we have there is a 3D plot of that in orange or gold, together with the x-axis in black, the y-axis in blue, the z-axis in yellow, and a curve where I have fixed the y value, but that is on our surface. And then the green is the slope of a tangent of that red point that you see there. Okay, and so what I'm going to do is describe the process of calculating a partial derivative with respect to x together with what that means. All right, so to understand what that means, let's change view so you can see this a little bit better, and let's change some of the parameters here. So as I change the value of the point, you can see changing the value of the point, I can calculate the slope of a tangent line at that point. Now, the partial derivative of the function f with respect to x is defined by this limit, and another notation for this is this symbol evaluated at the point AB. Okay, so this is the slope of a tangent line at our point AB. But that point AB has a z value as well. Okay, so we have A, B, and then the z value is f of AB. All right, so when we're calculating the partial derivative of f with respect to x, you can see that this red curve here is a cross section that is parallel to the x-axis. All right, if I rotate that, you'll see that it's parallel to the x-axis. So when I'm calculating the slope of a tangent, which is that partial derivative with respect to x, I'm calculating the slope of a tangent along that cross section that is parallel to the x-axis. But I can move this, right? And as I move that, it's still parallel to the x-axis, but notice the slope of that tangent does not change. It's the same irrespective of what value I choose for the y-coordinate. The slope, the number given by the slope, is changing when the value of x changes. So you can see I'm shifting the value of x forward and backward. And so the slope changes. It gets steeper as I increase the value of that point. Okay, so when we go ahead and calculate the partial derivative of f with respect to x, what we're doing is calculating the slope, fixing the value of y. In other words, treating the value of y as a constant. Okay, so let's jump straight into some example problems. So let's start with question number 1. Calculate z subscript x, where z is equal to 9x power of 6 minus 3y to the power of 5. Okay, so I'm going to do this in two ways. The first way, I'll just use the basic formulas, treating y as a constant and differentiating this with respect to x. And then let's use the definition and show that we get the same thing. Okay, so first, z subscript x is 9 times 6, x to the power of 6 minus 1, and then plus 0 because we are treating this as a constant. And so the derivative of a constant with respect to x is 0. Okay, so simplifying this, we have 6 times 9 is 54, x to the power of 5. And that's the partial derivative of z with respect to x. Okay, so now let's use the limit definition. So we have the limit as h goes to 0, 1 over h, z of a plus h, comma b minus z of a comma b. Okay, so simplifying this, so replacing that x with a plus h in there, we have 9a plus h to the power of 6 minus 3b to the power of 5. And then we subtract, so I'm putting a bracket in, we subtract 9a to the power of 6 minus 3b to the power of 5. Okay, so simplifying this one, well, we can see that the minus 3b to the 5th and the plus 3b to the fifth, those will vanish. And so what we have then is 9a plus h to the power of 6 minus 9a to the power of 6. So we can expand this by hand, but let's just use Mathematica to expand that because it's fairly easy to do that. So I'll say expand 9a plus h to the power of 6, and then subtract 9a to the power of 6. Okay, so this is what we get, but you can see it's a bit of a mess. So let's then divide that by h and factorize the result. Okay, and so this is what we have. So now let's write that down in our next line, and there we go. Okay, so now taking the limit as h goes to 0, everywhere where we see a h, we can now just replace that with 0. So we have 9, 2a squared, 3a squared. And then just expanding this, which is rather easy here, we've got 2 times 3 is 6, 6 times 9 is 54, a to the power of 6. And so what we have calculated is z subscript x at a comma b. Okay, and so then we learn that z comma x at x comma y, which is what we calculated up here. Oh, that is a power of 5. Okay, so let's change that to the power of 5. A to the 1, a to the 2, a to the 2 is a to the power of 5. And so we've got 54x to the power of 5, which agrees with what we got here, where we simply calculated the derivative of that polynomial treating y as a constant. Okay, question 1, part B. We've got z equals 9x to the 6th minus 3y to the 5th. And this time we're asked to calculate z subscript y. And so here we're treating x as a constant, x is the other letter other than y. So we can break this up. The derivative of a sum is the sum of the derivatives, and a constant can go through that differential operator. Okay, and so we have this. Now, we are treating x as a constant, so the derivative of this is 0 because the derivative of a constant is 0. So we have 0 minus 3 times y to the 4th and times 5. We bring the 5. Okay, so this is minus 15 y to the power of 4. Okay, question 2. Okay, so calculating z subscript x, we differentiate this with respect to x, meaning that we are treating y as a constant. So we have 3y cubed times the derivative with respect to x of x squared minus 3 times the derivative with respect to x of x plus 0, because this does not have any x's in it. Okay, and so simplifying this derivative is x squared, so 3y cubed times, 2x to x, okay, and then minus 3 times 1, and so we get 6xy cubed minus 3 for z subscript x. Now let's do z subscript y. So this time we are treating x as a constant and differentiating with respect to y. So we have 3x squared times the derivative with respect to y of y cubed minus 0 plus 4 times the derivative of y with respect to y. Okay, and so we get 3x squared times 3y squared plus 4, and so simplifying this, that's 9x squared y squared plus 4. Okay, so now let's get Mathematica to check both of those. So I'll enter z into memory symbolically. All right, and then I use uppercase D, differentiating with respect to x, uppercase D, differentiating z with respect to y. Let's see what we get. So for the first one, it gives 6x y cubed minus 3, so that's correct. The second one is 9x squared y plus 4, so that's correct. Okay, great. So moving on to question 3. We have x squared e to the power of 5xy. Okay, so it's clear that we're going to need to use the chain rule and the product rule. Okay, so let's just remember what the product rule said. Okay, so there's the product rule, and we're also going to need the chain rule, and so there's the chain rule. Okay, so let's differentiate this first with respect to x. So z subscript x is the derivative of x squared e to the 5xy with respect to x. So here we see that we need to use the product rule because this is a product of two things. So it will look like this, where the derivatives are partial. So we have, let's call this one v and this one u. So we pull one of those out, and then we swap the role of these. Oh, hang on. Whoops. Draw a line to separate these. Okay, great. So let's simplify this line now. So the derivative of x squared with respect to x is 2x. Let's put that in front. And then for this, we need the chain rule for this one. So we're differentiating e to the power of u, where u is 5xy, with respect to x. But using the chain rule, this is what it looks like, where u is equal to 5x. Y. Okay, so simplifying this line, z subscript x is 2x e to the 5xy plus x squared e to the u, and then times the derivative of 5xy with respect to x partially. Okay, so we're treating y as a constant, and so that is 5y times the derivative of x with respect to x, which is 1. Okay, so simplifying this, we have 5x squared y e to the u, but u is 5xy. Okay, and there we have our answer to z subscript x in question 3. So now let's do z subscript y, which is arguably a little bit easier because this time we don't need to use the product rule because x is the other letter, right? So that can float through that operator. So we have x squared times the derivative with respect to y partially of e to the 5xy. So we still need to use the chain rule here, but we don't need to use the product rule there. All right, so this is x squared times the derivative of e to the u with respect to u times the derivative of u with respect to y. But u, in this case, again, we can use the same u, that's 5xy. Okay, simplifying this derivative is e to the u. This derivative here, we're treating x this time as a constant, so that is just 5x. Okay, and so we have 5x cubed e to the 5xy. Okay, question number 4. So differentiating with respect to x, we have this. Now, y is treated as a constant, so that can float through that differential operator to its left-hand side. And so we're just differentiating cos of 2x with respect to x. But we need to use the chain rule here. So let's say let u be equal to 2x. Okay, and so differentiating cos of u with respect to u gives minus sine of u. Let's put the minus in front. And the derivative of 2x with respect to x is just 2. Okay, so simplifying this one, 2 times 3 is 6. So we have minus 6y sine of u, but u is 2x. Okay, and so there is z subscript x. Now differentiating with respect to y. So here we don't need to use the product rule because cos of 2x, since x is not y, all of this can be treated as constant and we can move that out in front of the differential operator, as well as that 3. So 3 cos of 2x times the derivative with respect to y of y. And of course, this derivative is just 1 right here. And so we get 3 cos of 2x for z subscript y. Okay, moving on to question 5. So z subscript x is the derivative with respect to x of x squared plus xy cubed to the power of 4. Now, let's let u be equal to that inside function, x squared plus xy cubed. We're getting ready to use the chain rule here. So this is the u to the 4th with respect to x, but let's use the chain rule. So this is what we have there. All right, now the derivative of u to the 4th with respect to u is 4u cubed. And then we have the derivative with respect to x of u, which is x squared plus xy cubed. Okay, so simplifying this derivative here, the derivative of x squared with respect to x is 2x, and the derivative of xy cubed with respect to x is y cubed, because remember, we're treating y as a constant. So we have 4u to the power of 3 times 2x plus y cubed. Okay, so that is z subscript x. Now moving on to z subscript y, differentiating with respect to y this time, x squared plus xy cubed to the power of 4. And so again, let's let u be equal to x squared plus xy cubed. And so we have the derivative of u to the fourth with respect to u times the derivative of u with respect to y. So again, the derivative of u to the fourth with respect to u is 4u cubed. And now we're differentiating this with respect to y. And so this part of it, the derivative of x squared with respect to y is 0 because we are treating that x as a constant. It's the other letter. So we have 0 plus 3xy squared. Okay, and so simplifying this, 3 times 4 is 12. Let's put the xy squared next. And then we have u cubed, but u is all of this. So that's x squared plus x y cubed all to the power of 3. Okay, there we go. Let's move on to question 6. So we have f is a function of x and y. It is 2xy minus x squared to the power of 5. So clearly here we want to let u be equal to our inside function, which is 2xy minus x squared. So we're going to use the chain rule here. So f subscript x is the derivative of u to the fifth with respect to x, but introducing the chain rule, we put u here, but u is this. Okay, and so now simplifying this, the derivative of u to the fifth with respect to u is 5u to the power of 4. The derivative of 2xy minus x squared with respect to x is 2y minus 2x. Okay, and so simplifying this, there's a common 2 there that we can factor out, and 2 times 5 is 10. So let's write this 10y minus x times u to the power of 4, but this is u. So we have 2xy minus x squared all to the power of 4. All right, and that is f subscript x. So now let's do f subscript y. So again, we have u to the fifth, put the y over here because we're going to use the chain rule. Okay, and so again, this is 5u to the power of 4, and then the derivative of this with respect to y is 2x minus 0. And so we get 10x u to the power of 4, but this is u. Okay, and then we're done with that question. Okay, fantastic. Let's move on to question 7. Z is equal to cos of x times y. So z subscript x is the derivative of cos of x times y with respect to x. But we need to let u be equal to our inside function, x times y. And so using the chain rule, we've got cos of u with respect to u times the derivative of u with respect to x. Okay, now the derivative of cos of u with respect to u is minus sine of u. And u here is x times y. And so we can treat that y as a constant. So this is just y. We have minus y sine of u, but u is xy. Okay, now doing the same thing with respect to y, we now want to use the chain rule again. Okay, and so simplifying this, the derivative of cos of u with respect to u is minus sine of u, and u is xy, but this time we're differentiating with respect to y. And so this derivative here will give us just x. So we have minus x sine of u, but u is xy. Okay, and so we're done with question 7. So let's move on now to question 8. Z is the sum of sine of x, cos of x times y, and then minus cos of y. Okay, so differentiating with respect to x, well, the derivative of sine of x with respect to x is cos of x. The derivative of cos of xy with respect to x, well, we've just calculated this above, so we got minus y sine of x times y, and then the derivative of minus cos of y with respect to x partially is just 0, and so z subscript x is cos of x minus y sine of x times y. Okay, so differentiating this with respect to y. Now, x is not y, so we can treat x as a constant, so this derivative with respect to y is 0. We have 0. The derivative of cos of xy with respect to y is minus x sine of xy, again from our previous question. And then the derivative of minus cos of y with respect to y is plus sine of y, because the derivative of cos of y with respect to y is minus sine of y, and two minuses give us a plus. Okay, so z subscript y is sine of y minus x sine of x times y. All right, now question 9. We have z equals 3xy minus x squared, and we're asked to calculate the partial derivative of z with respect to x at the point 1, minus 2, minus 7. And so that involves just subbing in 1 and minus 2 into the derivative that we get. So differentiating z with respect to x gives 3y minus 2x. Okay, and now substituting in 1 minus 2. Now, incidentally, minus 7 is superfluous here because when I sub in 1 and minus 2 into this, I'm going to get minus 7. Okay, I don't want to be wrong here. So let's go to Mathematica. I'm going to write this as a function here. Okay, I need to clear all z. Okay, yeah, we do get minus 7, so that's fine. So this is just 3 times minus 2 times 1. And so we have minus 6 minus 2, which is minus 8. Okay, confirming that with Mathematica. And yes, Mathematica also gives us minus 8. Okay, so now differentiating z with respect to y, we have 3x minus 0, and so we just get 3x. So now substituting in our point, we just have 3 times 1, which is 3. Okay, confirming this with Mathematica. Again, we have question 10. So we have z equals x squared times cos of 4y, and we are going to calculate the derivative of z with respect to y and then sub in the values x is 2 and y is pi on 2. Okay, so differentiating this with respect to y, x is not y, and so we can treat the x squared as a constant. So then we're differentiating cos of 4y with respect to y. Now we need to use the chain rule for that, so we let u be equal to 4y. So we have the derivative of cos of u with respect to y, but using the chain rule, we differentiate this first with respect to u and then multiply by the derivative of u with respect to y. So the derivative of cos of u with respect to u is minus sine of u, so minus x squared sine of u. And then we multiply that by the derivative of 4y with respect to y. Okay, so this derivative is 4, and so we get minus 4x squared sine of u, but u is 4y. All right, so this is the derivative of z with respect to y. And so the last part of this that we need to do is substitute in x is 2 and y is pi on 2. So this is minus 4 times 2 squared sine of 4 times pi on 2. And so 4 times 4 is 16. So we have minus 16 sine of pi on 2 times 4, which is 2 pi. So sine of 2 pi is 0. And so we just get 0 for this. Okay, question 11. So this says find all the second partial derivatives in this problem. So z subscript x is 6. No, it's 2y cubed minus 6xy. Okay, and then differentiating this again, that xx is the partial derivative of this with respect to x, and so we get 0 for the partial derivative of 2y cubed with respect to x, and then minus 6y, and so zxx is minus 6y. Okay, now z subscript y is the derivative with respect to y of 2xy cubed minus 3x squared y, and so we have 6xy squared minus 3x squared for that. Okay, differentiating that again gives us 6 times 2 is 12. xy minus 0, and so we have 12xy for that. Okay, so next, zxy. What is this? This is zx differentiated with respect to y partially, and so that is the partial derivative with respect to y of, looking up here, 2y cubed minus 6xy. And so we have 6y squared minus 6x. So this is zxy. Similarly, we can calculate zyx, which is zy differentiated with respect to x. So zy is here. And so for this, we get 6y squared minus 6x in agreement with zxy. All right, so let's scroll up to where I have just Clairaut's theorem stated, which says if f and its first and second partial derivatives are defined and continuous, then fxy is equal to fyx. Okay, so in this case, that's true. These are equal. All right, moving on to question 12. Okay, so differentiating this function with respect to x, we have y to the minus 1 plus, now the derivative of e to the x is e to the x sine y. We're treating as a constant, so this is e to the x sine y. Okay, differentiating with respect to y, because we're going to need this. So we have x times the derivative of y to the minus 1, so minus x y to the minus 2, and then plus e to the x times the derivative of sine of y with respect to y, because remember, we're treating x as a constant. So the derivative of sine of y with respect to y is cos of y. Okay, so now let's calculate zx, which is the derivative with respect to x of zx. Okay, so differentiating this partially with respect to x gives 0 for this one. And then the derivative of e to the x is e to the x sine y. We're treating as a constant, so we have e to the x sine y again. This is zx. All right, zyy is the derivative with respect to y of zy. Okay, so differentiating minus x y to the minus 2, the minus 2 comes down, so we have plus 2 x y to the minus 2 minus 1, which is minus 3. Now, differentiating e to the x cos y, we treat e to the x as a constant because x is treated as a constant, and we differentiate cos of y with respect to y and get minus sine of y. So minus e to the x sine of y. And this is zyy. Okay, next let's calculate zxy. So this is zx differentiated with respect to y. Now zx is up here. Okay, so differentiating y to the minus 1 gives minus y to the minus 2. Then differentiating e to the x sine y with respect to y partially gives e to the x cos of y. This is zxy. All right, now zyx should be the same by Clairaut's theorem, but let's just check. So we're differentiating with respect to x, z subscript y. Okay, and so differentiating this with respect to x gives minus y to the minus 2, because the derivative of x with respect to x is 1, and minus y to the minus 2 is treated as a constant. Now differentiating e to the x times cos of y with respect to x gives e to the x cos of y. And so you can see that matches this line. So we see this is zxy as well, in agreement with Clairaut's theorem. Okay, question 13. Two resistors R1 and R2 are placed in parallel and have a combined resistance R subscript T, given by R subscript T is R1 to the minus 1 plus R2 to the minus 1 all to the minus 1. And it says calculate the partial derivative of RT with respect to R1. Okay, so we are differentiating with respect to R1, R1 to the minus 1 plus R2 to the minus 1 all to the minus 1. So we need to use the chain rule for this. So we'll let u be equal to r1 to the minus 1 plus r2 to the minus 1. And so we have the derivative of u to the minus 1 with respect to r1. Using the chain rule, change this with respect to u, but we need to multiply by the derivative of u with respect to r1. Okay, so this is by chain rule. Okay, so the derivative of u to the minus 1 with respect to u is minus u to the minus 2, and then we multiply by the derivative with respect to r1 of u, which is r1 to the minus 1 plus r2 to the minus 1. Okay, simplifying this derivative, we have minus r1 to the minus 2 plus 0. And so this simplifies as u to the minus 2, which is r1 to the minus 1 plus r2 to the minus 1 all to the minus 2 times r1 to the minus 2. Okay, now we can notice here that there's another way to express this, because this is RT squared, and this we can write as 1 on R1 squared. And so in other words, RT over R1 all squared. That's another way to write it, but this up here is perfectly fine. Okay, question 14. We have f of x and y is x to the 4th plus 5xy cubed. And so we are asked to find the first partial derivatives of the function. So we want f subscript x is the derivative with respect to x of x to the 4th plus 5xy cubed. So that's 4x cubed plus 5y cubed. Okay, now f subscript y is the derivative with respect to y of x to the fourth plus 5xy cubed. So we have 0 plus 5x times 3y squared, which gives us 15xy squared. All right, question 15. Okay, f subscript x is 2xy minus 0. And so we just have 2xy. F subscript y, differentiating this with respect to y, gives x squared minus 3 times 4 is 12, y to the power of 3. Okay, question 16. F is a function of x and t given by t squared e to the minus x. So differentiating with respect to x, we have t squared times the derivative with respect to x of e to the minus x. Now that needs the chain rule, but what we'll get with u equal to minus x, the minus will come down. So minus t squared e to the minus x. Okay, now differentiating that with respect to t, we can treat the e to the x as a constant, bring that out in front, differentiate t squared with respect to t, and we get 2t e to the minus x. All right, question 17. F of x and t is the square root of 3x plus 4t. Now notice that we can write this as 3x plus 4t to the power of 1/2. Okay, so f subscript x is the partial derivative with respect to x of this. Now this needs the chain rule, so we're differentiating u to the 1/2 with respect to x, but using the chain rule, this is the derivative of u to the half with respect to u times the derivative of u with respect to x, but u is 3x plus 4t. So we have 1/2 u to the minus 1/2 times this derivative, which is just 3. And so we have 3 over 2 3x plus 4t to the power of minus 1/2, which can be written as 3 over 2 times the square root of 3x plus 4t. Okay, now differentiating that function with respect to t, well, the only difference here is where we got the 3. If we were to differentiate this with respect to t, we would get a 4 instead. So we can clearly see just by looking at this that f subscript t should be 4 over 2, which is 2 over the square root of 3x plus 4t. Okay, just by looking at that. So let's move on to question 18. Okay, use implicit differentiation to find dz on dx and dz on dy. These are partial derivatives. So we have x squared plus 2y squared plus 3z squared equals 1. Now look, we don't have a formula here for z in terms of x and y. Instead, we have an implicitly defined surface, just an equation. All right, and so yes, we could solve for z here, but when we do, we would get a plus or minus, right? And so in this case, it's easier to use formulas for implicit differentiation. So what we want to do is let f, uppercase f, be a function of x, y, and z. And so we just get it by taking this 1 over to the left-hand side so that we have 0 on 1. So x squared plus 2y squared plus 3z squared minus 1. So if f of x, y, and z is equal to 0, then the point x, y, z is a point of that surface. Okay, and so our formulas for the partial derivatives implicitly is dz on dx is minus f subscript x over f subscript z. Now notice the letter here at the bottom matches this letter at the top. This letter at the bottom matches this letter at the top. Okay, and so we need to differentiate this. Now also we have dz on dy, because we're also asked to calculate that. We have minus f subscript y over f subscript z. So we need to calculate the 3 partial derivatives of f with respect to x, with respect to y, and with respect to z. So let's do that here. F subscript x is 2x, and then plus 0, plus 0, plus 0. Okay, f subscript y is 4y, differentiating this with respect to y. The other derivatives are 0 because we're treating those letters as constants when we differentiate. And f subscript z is 3 times 2 is 6z. Okay, so now that we have that, the z on dx is minus 2x, taking the fx is 2x over fz, so 6z, and so we have minus x over 3z. Okay, dz on dy is minus 4y over 6z. Simplifying this, we can cancel a common 2, so we get minus 2y over 3z. Okay, So we're done with question 18. So let's move on now to question 19. So our first step here is to define f of x, y, and z. X squared minus y squared plus z squared minus 2z minus 4. Okay, differentiating partially, we have 2x for f subscript x. F subscript y is minus 2y. And f subscript z is 2z minus 2. So using our formulas, so dz on dx is minus f subscript x over f subscript z, which is minus 2x over 2z minus 2. And we can simplify this, canceling a 2, but we can also put this minus, multiply the minus by that bottom expression or denominator. And so we can call this x over 1 minus z. Okay, derivative of z with respect to y partially is minus f subscript y over f subscript z. And so we have minus 2y over 2z minus 2. And so this simplifies as canceling the common 2's, we have y over z minus 1. All right, so moving on to question 20, find all second partial derivatives of that function. All right, so differentiating f with respect to x, we have 4x cubed y minus 6x squared y squared. With respect to y, we have x to the fourth minus 4x cubed y. Differentiating fx again with respect to x, differentiating this line. And so we have 12x squared y minus 12x y squared. Okay, fxy is the derivative with respect to y of f subscript x. So this gives 4x cubed minus 12x squared y. Now differentiating fy with respect to x should get the same thing as this by Clairaut's theorem. Let's just check. 4x cubed minus 12x squared y. Yes, that matches. Okay, so what remains here is fyy. So differentiating this line, x to the fourth minus 4x cubed y, that's fy. So we have 0 minus 4x cubed, and so fyy is minus 4x cubed. Okay, so that's all of those second derivatives, all four of them. Question 21. So z is equal to y over 2x plus 3y. And we're asked to find all second partial derivatives. Okay, so zx. Now y is not x, so I can treat that as a constant. Pull that out the front, differentiate with respect to x, 2x plus 3y to the power of minus 1. Okay, so now we need to use the chain rule on this, but what that will do is we will differentiate this with respect to that inside, and so we have minus y, 2x plus 3y to the minus 2, and then multiply that by the derivative with respect to x of the inside function. Okay, and so simplifying this, we just have 2 for this part. So minus 2y, 2x plus 3y to the minus 2. All right, because I don't want to get this wrong, I'm going to get Mathematica to do the same calculation. Okay, and so yes, Mathematica gives us the same thing for that. Fantastic. So let's differentiate with respect to y now. This one looks like it's going to be a bit more tricky because suddenly we need to use the quotient rule for this one. Okay, so the numerator is our u, the denominator is the v. So we have 1 on v squared, v, du on dy, but this is dy on dy because u is y, and then minus the other way around. Minus y d on dy of 2x plus 3y. Okay, so simplifying this, 1 on v squared, where v is 2x plus 3y, and u is y. Okay, so 1 on v squared times, in brackets, 2x plus 3y, and then we subtract 3y. And so we have 2x over v squared, but v, remember, is 2x plus 3y, and then that gets squared. Okay, so there's zx and zy. Okay, so continuing, we're calculating all of the second order partial derivatives for this function. And so we need to differentiate zx again. So zxx is the derivative with respect to x of this. And so since minus 2y can be treated as a constant, or is treated as a constant, we are differentiating with respect to x of 2x plus 3y to the minus 2 and allowing that minus 2 to come through that differential operator. And so now for this part, we need the chain rule. We know how that works. Minus 2 comes down. We subtract 1 from that exponent, and then we multiply by the derivative of the inside with respect to x partially. Okay, so simplifying this derivative here is 2. So we end up with 2 times 2 times 2 is 8 times y over 2x plus 3y cubed. Okay, now differentiating zy again. We're differentiating this. Now this one's going to be very similar. So the 2x can come out. Okay, and so on this we use the chain rule. It means that 2 comes down. So we have minus 4x, 2x plus 3y in brackets to the power of minus 3. We're subtracting 1 from that exponent, and then we multiply by the derivative of that inside function. And so in this case, that derivative is just 3. And so we end up with minus 12x over 2x plus 3y cubed. Okay, so now this question says find all the second partial derivatives. So we're just missing zxy and zyx. So zxy is the partial derivative with respect to y of zx. And so here we need the quotient rule. Okay, there's a square in there, so be careful because we have a 1 on v squared. So in the numerator, we have u is minus 2y and v is 2x plus 3y all squared. So our derivative is 1 on v squared, v du on dy minus, we swap these around. Be very careful here. Okay, so you can see that this is quite tricky. So the derivative of minus 2y with respect to y is minus 2. We have 2 minus signs here, so let's call that plus y. Now we need the chain rule on this. The 2 comes down, subtract 1 from the exponent, which just gives this to the power of 1. And then we multiply by the derivative of the inside function with respect to y, which is 3. Okay, so now we just have to simplify that. So we have 3 times 2 times 2 is 12. So 12y, 2x plus 3y minus 2x plus 3y squared. And then that's all over v squared. This is v up here. So it's over 2x plus 3y to the power of 4. Now we can clearly simplify this a bit, right? Because we can expand that numerator really carefully and simplify. So 24xy plus 36y squared, 2x all squared is 4x squared, then times 2 is minus 8, so minus 8x squared. Okay, the product of 2 and 3 is 6. Then multiply that by 2, you get 12. And then another 2, you get 24. Minus 24xy. And then 3 squared is 9. 9 times 2 is 18. So minus 18y squared. And then this is all over 2x plus 3y to the power of 4. Okay, nearly done with that calculation. So 24xy minus 24xy gives no xy's. 36 minus 18 is 18. So we have 18y squared minus 8x squared over 2x plus 3y to the power of 4. Okay, and this is zxy. I'm going to leave zyx to you as an exercise to try to get the same thing. But just to keep me honest, let's go to Mathematica and I will calculate all of the required derivatives here symbolically. Just make sure we get the same thing. Okay, so Mathematica has given us, oh no, I see. So let's simplify this a little bit more. Okay, because we can pull out a 2 and then we have 9y squared minus 4x squared over 2x plus 3y to the power of 4. And so this up here is a difference of 2 squares. So we have 2 3y plus 2x, 3y minus 2x, all over 2x plus 3y to the power of 4. And so we can cancel one of these because these match. And so we've got 2 outside of 3y minus 2x over 2x plus 3y to the power of 3, having canceled one of the. Okay, and so now this matches what Mathematica gave us when we factorized that derivative.